Hey, I'm glad you're still with us on this journey through prime numbers. In the last video, we introduced prime numbers, introduced the sieve of Eratosthenes to help us find prime numbers, and we looked at some other interesting things that revolve around primes. So today we're going to continue with prime numbers and some of the offshoots with those. We're going to look at how to use them to find certain values, and we're also going to look at some of the cool theorems and conjectures. We're going to look at some of the research that's out there. All kinds of good stuff ahead. So starting out, first we're going to look at a topic that you've seen before. You probably saw it in 4th grade. Finding the greatest common divisor, also called the greatest common factor. And we're going to follow this up in a little while with the least common multiple. Those usually go together. But we're going to look at how to find these using your prime numbers. All right, so starting with the greatest common factor, that is the largest natural number that will divide evenly into every number in a particular set. And if we want to use prime factors to find it, we do the prime factor trees, and we go ahead and write the prime factorizations using exponents. And then we go through and we look for the ones that are in common, and we use the one with the lowest exponent. Multiply all of those together, and that product will be your GCF, also known as your GCD. So we're going to go through and look for those. We're going to look at the ones that the lowest exponents and use those. Okay. So let's look at the pair 12 and 21. With those two numbers, in probably the original way you were taught to do this, you would have taken 12 and listed all of its factors. 1 times 12, 2 times 6, 3 times 4. And then you would have taken 21 and listed its factors. 1 times 21, 3 times 7. And you would have looked at, well, what do they have in common? They have 1 in common, they have 3 in common, and that's it. So you would have been able to say, oh, okay, so my GCF is 3. That was one way you did it. But we're going to do a prime factor tree way, and different way of getting there, but we'll get the same answer. We'll get that the GCF is 3. So we're going to take 12 and 21 and first find the prime factors. Let's see, 12, I'm going to use 3 times 4. Remember, if you started out with like 2 times 6, that's fine. In the long run, you'll have the same thing as me. 3 is prime, I bring it down. 4 becomes 2 times 2. So I have 2 squared times 3. Then for 21, that breaks down to 3 times 7, and that's it. All right, so between those two, I like my colors here, I have the 3 in common. And remember, when you have a 3 in common, if you have something in common, you only use the one that has the lower exponent. So since they have 3, they both have just 3, so our GCF is 3. And that's it. You're like, oh, okay. So that, that in that case, the old way, the first way, the way on the left, the way on the right, they take about the same amount of time. But if your numbers involve bigger factorizations, you're going to like the prime factor tree. It's going to be faster and easier. All right. Next example I have circled here I'm going to do is for 120 and 240. Now, if you'd like to go through and list all the factors of 120 and all the factors of 240, be my guest. Although you might find it takes a few minutes, because 240 is starting to get to be a bigger number. So it might take you a little while. It's not impossible, but I really think the prime factor trees are faster. So I'm going to do those. All right, for 120, I'm going to break that down into 2 times 60. 2 comes down. 60 becomes 2 times 30. The 2's continue to come down. 30 is 3 times 10. The 2's and the 3 come down. And 10 is 2 times 5. And for 240, that's 2 times 120. So since I already know how 120 breaks down, I don't need to do any more. So I end up with 2 cubed times 3 times 5 underneath the 120. And I end up with 2 to the 4th times 3 times 5 under the 240. All right, so I've got a lot of stuff in common here. I do have a 3 in common. So a GCF, they're both 3, so I'm going to use the 3. I have a 5 in common, so I'm going to use the 5. And then with the 2's, one of them is 2 cubed and the other is 2 to the 4th. So remember, we're going to go with the lower exponent. We're going to go with the 2 cubed. Because you're basically just trying to find everything in common. So they have 3 2's in common. That extra 2 under the 240 is not in common, so we're going to not use it. So you multiply all that together. You already know that 2 cubed times 3 times 5 is 120, because that's what we had earlier when we did our prime factor tree for 120. It broke down to 2 cubed times 3 times 5. So it turns out the GCF of 120 and 240 is 120. Okay, let me do one more example. This time we're going to have 3 numbers, 18, 78, and 198. 18 will break down to 2 times 9. 2 comes down. 9 will break down to 3 times 3. 78, there's, again, you can start however, whatever you spot first. I just spotted 3 times 26 when I was looking at it. You might have spotted 2 times 39 first, whatever. 26 will break down to 2 times 13. Okay, then 198. These 2 is probably the easiest one to spot. 2 times 99. Then 99 breaks down to 9 times 11. And 9 breaks down to 3 times 3. And there you go. So let's rewrite these with exponents. We have a 2 times 3 squared. We have a 2 times 3 times 13. And then we have a 2 times 3 squared times 11. All right, what do all 3 have in common? All 3 have a 2. So we're going to go with the 2. And all 3 of them have 3's. But the lowest exponent is a 3 to the 1st. So we're just going to use a 3. We don't want the 3 squared because they don't all have 3 squared in them. We want the greatest common factor. The 11 is only in one of them. The 13 is only in one of them, so we're going to just skip those. So 2 times 3 gives us 6. So the GCF for 18, 78, and 198 is 6. Now if you'd gone through and listed all your factors of 18, 78, and 198, 6 would have been the biggest one they all 3 had in common. Now related to greatest common factor, if you have 2 numbers and their greatest common factor is 1, then you can say that those numbers are relatively prime. 3 and 13 are an example of this. Because if you look at 3, that's just 1 times 3. And if you look at 13, that's 1 times 13. And they both just have 1 in common. So they're said to be relatively prime. And in this case, 3 and 13 each are prime numbers. But they're also relatively prime because they're prime relative to each other. And relatively prime numbers don't have to be prime. They can be composite. It all comes down to that greatest common factor being 1. Let's see. I was trying to think of another example. Do I have a blank slide? Yes, I do. Like let's say you have 4 and 5. 4, you have 1 times 4 and 2 times 2. I'll do it the old-fashioned way. And then 1, you just have 1 times 5. So notice that 4 is composite, 5 is prime. Yet, when you look at their factors, the only thing they have in common is 1. So these are relatively prime. Even though 4 is composite, that part's fine. You're looking at the GCF in order to make your decision on that. So that's kind of a cool, oh, I just discovered I have more colors. I didn't realize that. That makes sense. There's 4 dots there, so that means there's going to be more options. All right, learn something every day. Okay, next we have least common multiple. The least common multiple is the smallest natural number that is divisible by all the numbers in a particular set. So in other words, if you take some numbers and list all their multiples, the least common multiple will be the first multiple they all have in common. And you can use your prime factorizations again. Real quick way of doing that is to do your prime factorizations, write them again with the exponents, and then this time you're going to list each prime factor with the greatest exponent that appears in any of the prime factorizations. The way I worded that's not the clearest on the slide. Sorry about that, but your book does a much better job. They say, list each prime factor with the greatest exponent that appears in any of the prime factorizations. Determine the product of the factors, then found in that step. Yeah, sometimes I try to reword things to make it the way it makes sense to me, and it's not always the clearest, but in this case, your book is the clearer one. All right, so let's revisit those same numbers that we just did for GCF, and let's do LCM of those. Old-fashioned way, I would have taken 12, and I would have thought about 12 times 1 is 12, 12 times 2 is 24, 12 times 3 is 36, 12 times 4 is 48, 12 times 5 is 60, 12 times 6 is 72, 12 times 7 is 84, 12 times 8 is 96, 12 times 9 is 108, 12 times 10 is 120. You know what? Let me pause. Let me do 21 for a minute. If I don't come up to anything in common, then we'll resume 12. But who knows? I might already have something in common. 21 times 1 is 21. 21 times 2 is 42. 21 times 3 is 63. 21 times 4 is 84. Ooh, there we go. There we go. There we go. The very first multiple they both have in common is 84. So that is the LCM. But we're going to do it with prime factor trees. We'll get the same result, just different way of getting there. Okay, so let me write 12 and 21 again. 12, I'm going to break it down to 2 times 6. 6, I'm going to break down to 2 times 3. So I have 2 squared times 3. 21, I'm going to break down to 3 times 7. So what we got to do is we got to look at all of the prime factors, not just the ones in common, all of them, and go with the lowest exponent on whatever pops up. 2 squared pops up once, so for the LCM, we'll go with 2 squared. That's the lowest exponent. It only pops up on 12, so that's the lowest exponent for you. 3 pops up in both of them. That's 3 to the first, so we'll just use a 3. 7 only pops up in one of them, but you go ahead and use it. So if you take any unique prime numbers and then go, if you see them appear more than once, go with the lowest exponent. And then multiply all that together. And you get the same result. So it works. A little different than GCF, because GCF you looked at what was in common, and then went with the exponent that went with that. But and I keep looking up at my computer. It has another thing, and I keep reading the wrong thing. What I just said was incorrect a minute ago. You go with the highest. If there's something in common, you go with the highest exponent. I apologize for that. That's the problem with having 2 devices going on at once. My computer has the GCD slide still up there, and I was glancing up and reading off that, and no, I'm doing LCM. Why? Yeah, GCF, you were looking for the one with the lowest exponent. Least common multiple. So what I was saying was you use all the unique prime numbers, so even they don't have to be in common, whereas GCF, they had to be in common. And then if you do have them in common, make sure you go with the greatest exponent for LCM. You'll see that in a minute. I'm going to do an example where it's going to come up. Sorry about that. Yeah, GCF, look for lowest exponent. LCM, look for highest exponent. If you're looking at what's in common. GCF only looks at what's in common. LCM looks at everything, all the different prime numbers that pop up. All right. It's also bad that I'm doing this late at night, but I'm like, I need to get another video in. With everybody working from home and being at school at home in my household, I don't get much time during the week to be able to make videos. So I'm trying to do this late right now on a Sunday night. And so words in my brain don't always get to my mouth correctly. All right, here we go. Let's do prime factor tree here of 120. We did it earlier, but right now I don't remember what it was. Okay, so 2 times 60. 60 breaks down to 2 times 30. 30 breaks down to 2 times 15. 15 breaks down to 3 times 5. So we have 2 cubed times 3 times 5. And 240 we know is 2 times 120. So that was the one where it's like, well, we know then it's 2 times all of the 120 factors also. So we ended up with 2 to the 4th times 3 times 5. And here's where that exponent fun comes in. Because remember earlier, like with GCF, we went with the lower exponent. So we looked at 2 cubed. But with LCM, where you look at the higher exponent, so we go with 2 to the 4th. And then we've got the 3 and the 5. 3 only is 3 to the 1st in each one, so we just use a 3 to the 1st. 5 is just a 5 to the 1st in each one, so we'll just use 5 to the 1st. So multiply all that together. Let's see, 2 to the 4th is 16. 16 times 3 is 48. 48 times 5 is 240. So the LCM of 120 and 240 is 240. So there's that one. Cool, huh? On the slide, I try to explain it as you're looking at, when you look at the common prime factors, use the one with the highest exponent. Like in this case, 2 cubed, 2 to the 4th, use the 2 to the 4th. And then if there's leftovers that you haven't considered yet, make sure you throw those in too. Like if there's something that's not in common, throw that in too. Let's do the 3 numbers one more time. The same 3 numbers. 18, 78, and 198. All right, we got 2 times 9. And we got 3 times 3 there. So we have 2 times 3 squared. 78, 2 times 39. 2 times 3 times 13. Then 198, 2 times 99. 3 times 33. 3 times 11. So rewrite those again with the exponents. We did those earlier, same numbers we did earlier, but now instead of GCF, we're doing LCM. With GCF, we only use the 2. We use that 2 there that they had in common. And then out of the 3's, there's a 3 squared, a 3, and a 3 squared. We had to go with the lower exponent, 3 first. But since we're doing LCM, it's a little different. All right, you have your 2's. So you're going to use a 2 there. And then out of 3's, your highest exponent is 3 squared. But then you also have a 13 and an 11. Like remember, you're using everything you can, not just what's in common. But if there is stuff in common, go with the higher exponent. So we have that. Let's multiply those together. And we get 2,574. And that's our LCM. So there you have it. So notice that the 13 and 11 got used in the LCM, whereas it did not get used in the GCF. Because they weren't in common for the GCF. But in the LCM doesn't care. If it's in common, go with the highest exponent. If it's not in common, throw it in there anyways. So there you go. Okay, moving forward. Little historical note. We're going to look more closely at this in a future video when we get to congruence. But just to mention, from 1977 to 2000, not that long ago, prime numbers were used as keys in encryption codes. There's something called the RSA algorithm that I'm going to introduce you to in a future video. And then with advances in computers, new systems keep getting developed for encryption. One of the ones that followed RSA was the Ryan-Dale block cipher, and that involved even more prime numbers. So like RSA algorithm uses products of large primes, which are very, like if you know the answer, like if you're trying to break the code and you know the answer after you multiply, it's really, if that number was found by just multiplying two prime numbers, it's really hard to break it down and factor it. Like our prime factor trees, we're using small numbers, so not too hard. You can try 2, try 3. But imagine if the first number you could try was like 5 digits. It would take you a while to try to figure out what goes in there. But as computers have gotten smarter and faster, and people have gotten smarter with these systems, they have to keep updating encryption standards. So like RSA algorithm's really old now. Too easy to break now. But we'll talk about that again. Another little historical note. There was a monk named Marin Mersenne. He's credited with the discovery of Mersenne primes. Mersenne primes are numbers of the form 2 to the n minus 1 that are prime. They were discovered in the 17th century by Mersenne. Turns out that if that exponent n is composite, then so is 2 to the n minus 1. So you can just skip putting any composite numbers up there. Like, don't bother trying to do 2 to the 4th minus 1, 2 to the 6th minus 1, 2 to the 8th minus 1. All of those are going to be composite. The key is the result has to be prime. So it takes prime numbers. But not all primes work. And that's the thing too. They have the Great Internet Mersenne Prime Search, also known as GIMPS. And you can participate if you'd like. If you go to that website there, you should be able to find some information. But you can volunteer your computer to do computing, and it's off time, like behind the scene, like in the background. But usually the people who discover the latest Mersenne prime are working with networks of computers or supercomputers or something else. But anyways, it coordinates computers across the globe to help search for larger and larger Mersenne primes. So your computer in the background could at least be helping with the computations, even if you don't become the computer to discover the next one. This was started by George Woltman, and then Scott Kurowski helped push it forward. I had to update this slide actually before I started doing this recording, because the project found the 51st Mersenne prime. The last time I had updated my slides, I think it was at the 49th Mersenne prime. So they found the 51st. That's the latest news. And it has nearly 25 million digits in it. Imagine that, dealing with a prime number. The number itself is not 25 million. It has 25 million digits. Isn't that crazy? But check out more of that website. I'm not going to go to the website because I'm on a video and I don't want to possibly have copyright issues. But you go check it out, read about it. It's pretty cool. Whenever there's a link mentioned, definitely check it out, because you never know when I might put quiz questions or test questions about something on there. But let's find some of our own Mersenne primes for a minute here. Remember 2 to the n minus 1. Oops. Okay. Try that again. Now remember, we can skip using composite numbers, because if you do something like 2 to the 4th minus 1, 4 is composite. 2 to the 4th is 16. 16 minus 1 is 15. 15 is also composite. That can't be a Mersenne prime because a Mersenne prime, by its name, has to be prime. And anytime you put a composite number there, it's going to come out composite. So don't even bother with those. But let's see here. Let's say we use 2. 2 times 2, because we have primes like 2, 3, 5, 7, 11. 2, 3, 5, 7, 11, 13, 17, 19, and so forth. There's, it keeps going. So if we did 2 squared minus 1, that would be 4 minus 1, which is 3. That's prime. If we do 2 cubed minus 1, that's 8 minus 1, which is 7. That's prime. If we do 2 to the 5th minus 1, that's what, 32 minus 1? 2 times 4, 8, 16, 32. That's 31. Still prime. If we do 2 to the 7th, that's 128 minus 1. 127. I believe that's prime also, but I have to stop and check real quick. 6, 7, 8, 9, 10, 11. Yeah, that's prime. Okay. I think the next one is not, though. I think the next one's composite. I was looking it up earlier. Let me see here. So 2 to the 11th is 2048. And then minus 1 is 2047. I think that was one of the ones that was not prime. But I don't remember. I'd have to go back and look. I don't want to take your time right now to check, but I'm pretty sure that one's composite. I said I don't want to take your time right now, but then here my mind's like, oh, this is a puzzle. I don't want to put it down. Oh, I love math. I love puzzles. I hate walking away from a good puzzle. Been trying. I'm up to 11, and so far that's not working. Yeah, I don't know. I think it might be prime. One pretty soon, either 11 or 13 is going to run into where you get a composite number. So then that's not a Mersenne prime. Like, it has to be prime. So not all primes work. But they're constantly on the search for the next Mersenne prime. A couple of really cool conjectures about primes. Goldbach's conjecture says that every even integer greater than or equal to 4 can be represented as the sum of 2 primes. If you'd like to play with some numbers and see what the Goldbach pairs are, that link there will take you to a nice little tool. And then there's a twin prime conjecture. Primes of the form n and n plus 2. This is an unproven statement saying that there are infinite number of pairs of twin primes. And there's a link there for information on twin prime research. And that link has a really funny, corny music video that I encourage you to watch. It's pretty good. And then if you want to know about very recent research leads on the twin prime conjecture, look up Chang and Tao and the Polymath Project, and there's quite a story there. I'll come back to it. Let's look at some Goldbach conjecture for a minute, and then we'll look at twin primes for a minute. All right, Goldbach conjecture. Every even integer greater than or equal to 4 can be represented as the sum of 2 primes. So let's just play with some even integers greater than or equal to 4. You have 4, 6, 8, 10, 12. Let's see. So you can at least find one pair of primes that'll add up to give you that number. And the prime can repeat. It doesn't have to be 2 different primes. It can be like on 10, you can have 5 plus 5. And that's perfectly legal in the Goldbach conjecture. 5's prime, and you can repeat it. All right, so 4, you have 2 plus 2. We can't use 1 plus 3 because 1's neither prime nor composite. Let's see, 6. 1 plus 6 doesn't work. 2 plus 4 doesn't work. 3 plus 3 does. 3 is prime. So 2 plus 4 doesn't work because 2 is prime, but 4 is not. So that's not a Goldbach pair. 8, can't use 1 plus 7. 2 plus 6 doesn't work. 3 plus 5 does. 4 plus 4 does not. 10, 1 plus 10 does not work. 2 plus 8 doesn't work. 3 plus 7 is another pair, Goldbach pair. So you can have more than one. When you start doing really big numbers on that calculator, it's kind of fun to watch the list grow. But the growth of the list doesn't necessarily follow a pattern. Like, you could do one big number and have this huge list, and then you could do another number even bigger, and maybe the list gets smaller. Like, the lists will change sizes. I'm sure there's some kind of research into that as far as like if there's a pattern to how many pairs there are, but I'm not aware of it. All right, so 4 plus 6 didn't work there. All right, 12. 1 plus 12 doesn't work. 2 plus 10 doesn't work. 3 plus 9 does not work. 4 plus 8 does not work. 5 plus 7 does. 6 plus 6 does not. So here's an example. We went up to 10 that had 2 pairs, but then we went to 12 up to 12, and that went back to only having 1 pair. So the numbers of pairs can flip-flop. But that's the Goldbach conjecture. So it's unproven, but everything they've tested so far fits this conjecture. Twin primes. Okay, so going back to twin primes, let me just list my primes again real quick. Just some small ones. 2, 3, 5, 7, 11, 13, 17, 19. There's more. But some examples of twin primes here include 3 and 5. See, 3 and 5 are twins because you have 3, then you have one number, 4, and then you have 5. So it's like 3 skip 5. Those are twin primes. In the definition, if n is 3, n plus 2 is 5. Another pair is 5 and 7. If n is 5, n plus 2 is 7. 7 and 11 are not twin primes because they have a lot more numbers in between. They have 8, 9, and 10. They have 3 numbers in between. But 11 and 13 are twins. They only have 12 in between them. 13 and 17 are not because they have 14, 15, and 16 in between them. But 17 and 19 are because they only have 18 in between them. Yeah, so that, for a long time, mathematicians were working on trying to prove it, to say that there's an infinite number of pairs of twin primes. Yitang Zhang is an interesting character. He had pursued his math education, but he was not able to get a professor position for a long time, and he was working all kinds of jobs, including making sandwiches at Subway. But he was continuing his own math work on his own time, and he was actually made a pretty big discoveries that once they were revealed, then next thing you know, he has a nice professor position. But he and Terry Tao have been working extensively on this twin prime conjecture, and what they've managed to do, Zhang started it and Tao's helped continue it, is that they haven't been able to prove totally that there's an infinite number of pairs of twin primes, but they've been able to narrow it down and say, okay, so like let's say we say, all right, there's prime numbers that are spaced 1,000 apart instead of just 1 apart like the twin primes. And they were able to prove that there's infinite prime number pairs like that. And then they were able to narrow it down and maybe say, there's infinite pairs of prime numbers that have 100 numbers between them. So they keep narrowing it down. So they haven't quite narrowed it down to the twin concept, but they've made a lot of progress towards narrowing it down really close. And then if they can keep making progress, eventually they'll be able to prove this conjecture. So if you look them up, you'll find a lot of information on them. It's kind of neat that there's so much math still going on. Terry Tao is a really interesting character if you read about him. Super genius. He, like when you read about these mathematicians, it seems like they all lived so long ago. He's like one of those Leonhard Euler or Isaac Newton types. He was already had his PhD by the time he was 16. And he leads this online, basically research type I don't know what to call it right now, but people collaborate online, and he leads it, his polymath project. And they've, with this project, this online collaboration, they've been able to do a lot of mathematical research at lightning speed, because it's like the whole hive mind concept, like everybody's working together and putting in in real time, 24/7, putting in their contributions. So that's been kind of fun to learn about. And Terry Tao too is kind of interesting, because he, being a genius and all, but he does still have a social life. Like, he's married, has young children, and all that. He's not, like, sometimes you read about these geniuses and they're recluses or whatever, but not always. Like, that's a faulty stereotype. He's actually got quite a life. Anyways, all right. Triangular numbers. These are fun, especially if you like shapes. Numbers that can be arranged in a compact triangular pattern are triangular numbers. You can find graphics at that link. Check out that link. There's a lot there, a lot of good information. The properties of these numbers were studied by the Pythagoreans. You've probably heard of Pythagorean theorem, a squared plus b squared equals c squared for right triangles. Pythagoreans were a group of scholars under Pythagoras, but they studied these triangular numbers extensively. Let me try to explain triangular numbers by first mentioning squares. You're likely familiar with, like, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, and so on, right? And I don't know if you've thought about it other than, like, finding area of a square. But, like, square numbers, you can draw dots and create squares. Like, 2 squared is 2 by 2, 2 times 2, and makes 4 dots. 3 squared is 3 by 3 dots, makes a square with 9 dots total. 4 squared, you make a square with 4 by 4 dots. It's kind of the concept too of, like, finding the area of a square. 4 dots by 4 dots, it's a square. 4 times 4, there's 16 dots. Well, triangular numbers, it's kind of that idea, but with triangles. You start with 1, and then you add 2 more, you get 3. Add 3 more, you get 6. Add 4 more, you get 10. And so on. So notice that each time you just add the next number. So, like, the next triangular number, you add 5. You would get 15. Next triangular number, you add 6. You'll get 21. Next triangular number, you add 7 and get 28. Next triangular number, you add 8, you get 36. And so on. So all of these triangular numbers you can draw with dots in a triangular shape. So that's what's kind of cool about them. Now, what if, though, if you were asked about the 100th triangular number? So, oh my gosh, how many dots are in the 100th triangular number? It's not 100. It would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, etc. Plus 99 plus 100, whatever that is. If only there was a formula for this. What the heck? That's a lot to add up. I mean, early on, that's easy. Like, the second triangular number, 1 plus 2, you get 3. The third triangular number, 1 plus 2 plus 3 is 6. Fourth triangular number, 1 plus 2 plus 3 plus 4 is 10. But I don't want to sit here all day and add up all the way to 100 and see how many dots there are and what that triangular number is. So let's look for a pattern. Let's take the triangular number 3 and turn it on its side. And let's change colors here. And let's do another, let's turn it on its side again and draw another one. Like that. What do we got? We have 3 times 2, which is 6. Okay. What if we do that with the 3 dots? All right. Or the 6 dots, sorry. The third triangular number. So let's turn it on its side. So we have 6 dots that way. But then let's like do the same thing. Same triangle, just flipped again. Sorry, I'm trying to think about this for a second. My head does not flip things very well. So I gotta think about this real quick, make sure I do this right. All right, 1, 2, 3, and then it's gonna be 1, 2, like that. Okay. So we end up with 4 times 3. Or 3 times 4 if you'd rather, which is 12. And for the one with 10, same idea again. Let's turn it on its side. Do it over here, starting to run out of space. All right, 2, 3, 4. I'm trying to count, make sure I don't mess up the drawing of this. I already messed it up. Make sure everything's lined up. Yep, I didn't need that one. Okay, so I turned that one on its side. So that's 4, 7, 8, 9, 10 dots. But then do this, like, do a mirror image of it. So the same triangle just flipped. And then add that over here. Like that. Well, that ends up being, what, 5 times 4? Or 4 times 5? That's 20. So when I do that, notice that, like, let's say n is the number of the triangle. So like, n is 1 for the first triangle, n is 2 for the second triangle, n is 3 for the third triangle, n is 4 for the fourth triangle, so on. N is 5 for the fifth triangle. Notice that in the second triangle, we have 2 times 3 is 6. Well, so that's like having n times n plus 1. In the next triangle, we have 3 times 4. That's like having n times n plus 1. 3 times 3 plus 1. Fourth triangle, we have 4 times 5 when we did the little rectangle thing. So n times n plus 1. But the little rectangle thing gives us double the dots. So if we want to figure out how many dots we actually have, we need to divide by 2. Because we want just the number of purple here. So making the little rectangle helped us find our pattern for our formula, but it gave us too many dots. The rectangles are too many dots, or twice as many dots. So the little pattern, nth triangle times the next number up, n plus 1, we have to then divide by 2 to go back and get, well, how many dots are truly in the original triangle. So for the 100th triangle, n is 100. You could do 100 times 101 over 2. And you get 5,050. Pretty cool, huh? But yeah, check out the website I listed on the slide back there. A lot more information there. A lot more cool patterns and stuff to check out. You'll start to see why I fell in love with geometry and number theory and things. All right, I mentioned a minute ago that the Pythagoreans like to look at the triangular numbers and study them. So let's add Pythagoras of Samos to your mathematician list. He founded a religious and philosophical school in southern Italy in 6th century BC with scholars known as the Pythagoreans. They were a super secret society, used a lot of protocols, much like how you would imagine like meetings with Freemasons and stuff to go. That's how they were. They were very, very big on equality. Men and women were admitted equally and treated equally. And then it's kind of funny because like Pythagoras is always credited with discovering the Pythagorean theorem, but more than likely it was his students in this group, the Pythagoreans. Somebody there figured it out, probably not Pythagoras himself, but he got the credit. That still happens nowadays with PhD candidates. They make this discovery in their research on their dissertation, but the person who's they're guiding their research is the one who gets the credit and gets their name on it. But anyways, so that's probably what happened there. And it's really funny because later archaeological discoveries figured out that the Babylonians already knew about the Pythagorean theorem over 1,000 years before Pythagoras even existed. Yeah, but Pythagoras didn't know the Babylonians knew it. History ends up repeating itself. All right, one more thing. Carl Friedrich Gauss. Why am I bringing him up? Another mathematician list guy, really neat person, often called the Prince of Mathematicians. That fundamental theorem of algebra, he proved that at the age of 22. It's pretty young for such a major discovery. When we get into modular arithmetic, you're going to see a symbol for congruence. Looks like a equal sign with an extra bar. He introduced that symbol when talking about congruence. And he also added the numbers 1 through 100 in his head at the age of 10. He was kind of a precocious kid in class, very smart, got bored easily, finished his work fast. And one day his teacher just kind of wanted to keep him busy, keep him from asking her so many questions. So she sent him off to add 1 through 100. He went off for like a minute and came right back with the answer. Did it all in his head. If you would like to try to figure out how he did it without me telling you, pause this video right now. Don't play it until you're ready to check your work, check your answer, or come back, or just give up and come back and find out how he did it. Okay, hopefully if you were going to go work on it, you did that and now you're back. Or if you're just like, nah, I'm just going to see how it works, that's fine. Video's still going. But yeah, somehow he added 1 through 100 in his head. He was able to quickly recognize a pattern. He noticed that on the extremes of things, he could add 1 and 100 and get 101. He can add 2 and 99, get 101. You can add 3 and 98 and get 101, and so on. 50 pairs of this, 50 101s means 50 times 101, which is 50/50. Does that look familiar? It should. Remember earlier I asked you about the 100th triangular number? Up there in the right corner? That's basically what we just did. Gauss's problem. 100th triangular number. N is 100. Got 100 times 101 divided by 2. Remember we had the n times n plus 1 over 2 for the triangular numbers? Well, in this case, the 100 over 2 is 50. 50 times 101 is 50/50. Same thing. But Gauss did this in his head super fast. So, pretty talented guy. But there you go. All right. Well, I think that wraps up as much as I want to ramble on about number theory for now. When we get back, we're going to be using some of these a few of these concepts that I touched on. I'm going to be skipping around in the book in the next few videos. So definitely pay attention to your assignment list. Also, definitely be looking in Canvas modules, because not only am I making these videos and posting links in there, but you're going to see links to other very important websites. There's videos and web pages, and you're going to want to watch those or read those, because that information will be covered on your tests and your final. So I'm not going to necessarily teach all of it in these videos. Definitely check your modules, look under the units, check out everything I have there. It's all important. All right. Well, thank you for joining me again, and I look forward to seeing you again or talking to you online.